How is it that all of the computing power of the entire Apollo mission fits on the smartphone in your pocket today, but the parachute systems used then are virtually the same as the ones that we use today? My name is Eugenia Behar, and along with my colleagues, I'm here to present to you all the Daedalus, a continuous disreefing mechanism designed to bring parachutes into the 21st century.
Thanks, Eugenia. So disreefing is the process of incrementally opening a parachute. As you can see in this video, the parachute is released at a reduced diameter, and after a certain amount of time, it's allowed to open to its full diameter. Disreefing has been done the same way since 1955. It basically uses several pyrotechnic line cutters mounted in the skirt of the parachute that are cued by a time delay fuse that allow it to proceed to the next stage. Disreefing is done to reduce the peak impulse that the capsule sees during its descent. So as you can see in this plot, if it were allowed to open all at once, the capsule would see a huge impulse, whereas if it's done in stages, it sees many small impulses. We propose a mechanism that opens the parachute continuously, further reducing the force that the capsule sees. This force leads to huge benefits for the system. So this is a 28% reduction in deceleration of the capsule, which means that we can bring more delicate payloads back to Earth safely. It also leads to a 28% force reduction, meaning that the loading on the structural architecture of the parachute system is drastically reduced. And significantly, it leads to 65% reduction in the time to full inflation of the parachute, meaning that the capsule lands safely for more failure scenarios, such as late deployment. This project was proposed to us by Tyler Schlenker. He's the lead of parachute systems for the Dragon at SpaceX, and we worked closely with Tyler and several of NASA's parachute engineers throughout the year. So right now, there's no such thing as a continuous disreefing mechanism for aerospace parachutes. There are a lot of patents in the area, or a few patents in the area, but none are sufficiently versatile for the aerospace launch envelope or viable enough for aerospace safety standards. We worked with NASA to outline some system characteristics such that our device would integrate seamlessly into their parachute system. This includes NASA's standard 2x safety factor, their maximum anticipated tension in the reefing line for their system, and the standard temperature envelope for aerospace launches. We also outlined system goals so that we would improve upon their existing system. So that's a reduced force and a time to inflate under 45 seconds. And with that, I present to you Daedalus, the world's first continuous disreefing mechanism for aerospace parachutes.
So Daedalus is suspended at the center of the parachute by 4 reefing lines. We do this to ensure that there's symmetric inflation and also to avoid the extreme vibrations experienced on the skirt of the parachute caused by flutter during deployment. The system uses integrated passive and active braking systems in order to control the velocity being let out to monitor the diameter of that parachute. Before we could design this, though, we had to understand the physics of the system. So in a parachute system, you have 3 main forces. You have the drag force of the parachute, the drag force of the capsule, and the weight of the system. We were primarily focused on controlling the drag force of the parachute and ensuring that that term remains constant. As you can see here, that's dependent on a number of factors, including the velocity of the entire system and the diameter of those parachutes. We thus set out to design a device that would control the diameter in order to keep this specific force term constant throughout the deployment. On the left, we have NASA data that shows 3 spikes corresponding to current disreefing stages. And on the right, we have the theoretical result of continuous disreefing through our mechanism. As you can see, we have to hold the parachute force at that initial opening diameter, as a 3% diameter is the theoretical limit of, the practical limit of reefing a parachute. Since the kinetic energy that has to be dissipated in both cases is the same, by holding our parachute force at a higher level for a longer period of time, we can ensure that we reach full inflation at a faster rate. Now, this thus means that we have a distinct trade-off between the maximum force experienced and the time to safe deployment. This allows our stakeholders to choose between various parameters as necessary. For example, in the case that there is a failed parachute deployment, rather than having extreme force spikes occurring as the velocity decays at a slower rate than expected, we can instead have our devices hold the parachutes at a constant force for a longer period of time, ensuring that safe deployment is achieved.
Our device, in essence, is the integration of two independent braking systems. First, we have a passive system which aims to reduce the force in the tension in the reefing line by 90%. Once the tension in the reefing line is reduced, it'll see our active braking system. This is a servo-controlled friction brake, which does the last 10% of the work. A capstan, in its simplest form, is a metal cylinder with a tension rope running around it. They're often used in naval applications to hold entire ships to docks. This is because they provide a huge mechanical advantage, where a small holding force can be used to sustain a massive loading force on the other side. And they do this through friction between the rope and the capstan itself. In our case, we specifically designed our capstans to reduce the force by 10 times. This is very important because it means that our friction brake has to do far less work. The active system is in essence a feedback control loop. An onboard GPS tells us the capsule's velocity, and from this we can calculate our ideal diameter of the parachute at any point in time. It knows our current parachute diameter from an encoder on our spool. The difference between these, it tries to account for by releasing and activating the brake. We have a servo which applies a torque to a gear train, which moves the brake pads in or on the brake disc, applying and modulating the force. It's this modulation of the force that allows us to control the letting out of the reefing line, and so get our ideal parachute diameter. The spool is designed in such a way that we can account for the 600 feet of reefing line rope that we need on our 116-foot diameter parachute. Additionally, it's mounted in two roller bearings, which provide the added benefits of applying some viscous damping. This means that the force that they apply to fight the rotation is proportional to the velocity at which they're spinning. This is important because in conjunction with our passive system, this means that even if our active system completely fails, we can still ensure a safe but suboptimal parachute deployment.
Now, in order to validate this system, we took our components apart into their subsystems and tested them each individually. We used the MTS machine in the basement of the town building and conducted a variety of pseudostatic tests on our variety of components. Here we were able to break down our system and ensure that each was able to perform its necessary function. The capstans, we were able to validate that 10 times force reduction. The spool and the servo were able to monitor the way that rope was actually coming off the line in real time. Taking all this information, we were able to combine and run an integrated drop test. Here you can see a 100-pound mass falling about 1.5 meters, and we're able to control at the speed at which it falls. The video on the left shows the mass falling, and the video on the right shows, if you look very closely, our control system. Here, the encoder on the spool is monitoring the speed at which the rope is being let out. When it hits a threshold velocity, the brake is engaged, stopping the mass from falling. This is one of many tests that we were able to conduct to demonstrate our control of the system. To further demonstrate our control, we built 3 dynamic Simulant models that ran in succession to one another. We started with our green model, which did the ideal diameter profile given an initial velocity and position. That model took into account the device's actual time, place, and speed, and conducted simple math to basically determine how the parachute should open throughout time. We took that as an input and applied it to our blue box, which is the Daedalus system itself. Here we took a lot of our pseudostatic testing characteristics and applied them to a realistic model that took that ideal profile and predicted a realistic one. In our orange box, we compared our realistic and ideal conditions, and were able to plot them on top of each other. Here in white, you see the ideal force and time profile of the parachute, of the diameter of the parachute opening. In red, you can see Daedalus's performance on top of it. Here we have about a 1% error, and as you can see, this is due purely to the realistic nature of our model. We were able to account for latency of our electronics as well as servo control time, which produces some time delay, which is what you can see here in the discrepancies.
So in order to make our mechanism space grade, there were a few modifications that we would make. The first is changing all steel parts and aluminium parts and making them titanium. Titanium has a much higher strength to weight ratio and also has a lower rate of temperature dissipation. Next, we would have larger viscous dampers. This would allow, in the case of an active brake failure or electronics failure, the capsule to return safely to Earth at a specified speed. Next, we would integrate line sensors to check the tension. Currently, as no one has ever created a continuously disreefing mechanism, nobody knows the tension in the reefing line. Therefore, using these sensors would allow us to obtain this data, which could be used in later tests. Lastly, we would optimize the volume, decreasing it to decrease its footprint in the overall packed parachute. So we are currently in the process of obtaining parachutes from NASA, and SpaceX has already agreed to do a drop test with our mechanism. Overall, the Daedalus system reduces the force on the capsule and reduces the time to steady state. We'd like to thank our advisor, Dr. Kevin Turner, our TA, Sam Altland, and Joe and Pete from the machine shop. We are Daedalus. Thank you very much for listening. We open the floor to questions.
Yeah, of course. So any system that uses a parachute would benefit from a continuous disreefing mechanism. Particularly, we've discussed the applications with the Army, so dropping large payloads from planes, particularly.
Yeah, the basic benefit is that when you reduce the load, you reduce the amount of material that you need to be absorbing that load, which thus means that for a given container size, you can basically put more payload in that. So in the military applications, that means heavier things can be dropped safely.
How does the deceleration force when the parachute opens compare to the deceleration force of actually landing on the ground or water or whatever?
Sure, I mean, so when the capsule currently lands, like the Orion, it lands, I think, at a speed around 5 to 6 meters per second. And that's something that we can't change. So, I mean, really our goal was we didn't want them to change their overall parachute system. And what's great about, I think, what we designed is it integrates straight into what they currently do. They don't have to change anything about their current parachutes. So, I mean, that's something that we can't really change, so.
So, I guess what I'm asking is, does it hurt more when the parachute opens compared to when you land on the ground?
Mm-hmm. Oh, yeah, because, I mean, yeah. So, so there's a
lot.
There's going to be a bump when you land, but there's a huge snatch force in the beginning, which is basically, it goes from falling just with gravity to this huge force that's pulling back on it.
You can kind of see here that the load eventually decays when it reaches a steady state condition. The issue is that you can't actually go that low with your initial load because the parachute has to be open to a finite diameter when it goes up, and that initial snatch has a pretty significant load. So we've designed the whole system around matching that practical minimum, which is a 3% reef diameter.
Do you have a feel for its reuse, like from one mission to the next?
Sure. So currently, the devices they use, these reefing line cutters, they're single use. And in a lot of ways, I think the entire parachutes are single use. So because when it goes up, a bunch of suspension lines get frayed. So the idea is we didn't design it specifically with reuse in mind. But theoretically, it could be. I think that's why it wouldn't be. Because they're like power cutters, basically destroy themselves. They fire off once and that's it. But ours could just be reloaded with rope. That's how we kind of did our test. It was like reload the rope and go.
Can you describe your physical testing of the apparatus?
Sure. So, I mean, the testing that we did was first on just the capstans, and this rig itself, the 8020 rig, was just built so we could test in the MTS machine, which can apply a high force. And so, I mean, the ideal test would be a drop test where you drop it from space and you see how it reacts. But of course, we couldn't do that. So, yet. So our best estimation was to apply the high force that the MTS machine can apply. And that's a speed control test. So you basically set a speed and you pull on it and you see how it reacts. And that proved to us that it can survive the maximum force that's going to see. And then the next big test was the drop test that we showed, which is sort of just showing that we have the control capability, which means that given any mass on the other side, we should be able to control the exact speed that it's going at by modulating our brake force.
What would you expect to learn during the real-world test that you haven't seen already in the prototype?
I think the biggest thing is actually understanding the way that the reefing line acts under tension. So the way it works right now, if I can take you to a calculation, the way they calculate reefing line tension presently is based on what's something called overinflation angle. And so basically, they take a lot of data from sensors that they have at different reefing stages, and then they take a lot of photos, and they basically figured out that the amount that the parachute overinflates is how much tension you get in that line. And so some preliminary estimates of what a continuously disreefed reefing line profile would look like is they basically took a number of these points and just kind of plotted a decaying curve through that. But realistically, we have no idea how it will actually perform. So I think the most interesting thing will be to learn how that works. What's cool is the way we've designed the system is that it's not worried at all about the forces. It's just worried about the profile as you go. So that force could be held constant at the 600-pound force that we're expecting. It could oscillate in crazy ways, and our device should just continuously adapt to handle that.
That's all the time.
Great. Thanks.
Thank you.
Thank you so much.